Okay, so good morning, everyone. Okay, nice to see all of you back here. All right. So today we are going to cover a few things. Okay. We're going to be finishing up on the last topic. The last chapter we did halfway through on Mutex concept. All right, and today we're going to finish up that chapter by discussing semaphores. All right, and after we're done with that, I'm going to go through with you the lab manual for semaphores to understand what uh, is expected and the behavior, okay, and why is it like that. All right, and after that we're going to go on to the next topic on flags, events, and message queues. All right, and I will try to also go through the next lab manual as well. All right, so that you have a good idea of all the different ways in which you can design your overall RTOS architecture. Okay, so on last Friday when I went around the lab, I saw most of you have already finishing up the assembly part. All right, and you can have messages sending from your Android phone to the board, and you are able to control LEDs, control motors, and so on. Okay, so now with the Lab 8 and Lab 9 concepts covered, all right, you already have all the once we cover that, you have a complete picture, correct, on all the different tools you have to design your whole architecture. All right, and then you can decide how you want to go ahead with framing your architecture and sending information between the different threads, synchronizing, and so on. Okay, so let's get started first. Okay, so in the last chapter, okay, the last lecture we went through Mutex. Okay, so let me just quickly go through the Mutex, one important concept, all right, to make sure everybody understands this well. Okay, can you all see the screen I'm sharing? Okay, good, thank you. Okay, so this is basically the Mutex code, okay, the very basic code where we say each thread has to acquire and release, all right, and then you control the LEDs. Okay, so if you were to run this code, okay, let me compile this. Okay, so let me bring up the camera here. Okay, so if I were to run this code, okay, we know the behavior. All right, we saw this last lesson where we saw that it will first flash red and then it will flash green. All right, so basically because once my red LED thread acquires the mutex, okay, it controls the red LED. And even though there is a OS delay, there's a context switch because of round robin, whatever happens, when I go to the other thread, okay, I must first get the mutex, then I can control the LED. Okay, and since the mutex is already held by the other thread, okay, I'm blocked until the other thread releases it, then I'm able to unblock and carry on running. Okay, so this is what we saw during the last lecture. Now let me do a change here in the code, and then let's discuss the behavior. Okay, so right now, as you can see, both LED red thread, LED green thread follow this mutex acquire and release. Okay, now if my LED green thread, I do not take the mutex. Okay, that means I comment off the mutex acquire and mutex release. Okay, my red thread acquires the mutex and controls the LED and releases the mutex, but my green thread does not acquire, does not release. Okay, and if let's say I go ahead and run this code, okay, what do you think will happen? Okay, so I have launched a poll. Okay, you can put your response there. Okay, so basically what I've done is, okay, the red LED thread is taking the mutex and releasing the mutex, all right, wrap around the LED control code. Whereas the green, I have removed the mutex acquire and the mutex release. Okay, I remove both of them. Okay, so if you have tried this in the lab on your own, okay, then you probably have an idea what would happen. Okay, so I'll give you a bit more time. Okay, but 80% have responded. Okay, so this is a very important concept you must understand. Okay, because many students have this concept wrong, and then everything goes haywire. All right, so you need to understand this concept very, very clearly. That's why this question is important. Okay, 193% have responded. Okay, I'll just end the polling now. Okay, and I'm sharing the results. Okay, so about 58%, okay, slightly more than half have said yellow. Okay, and only repeat yellow. The rest have a few different ideas. Okay, so let's see what will happen. Okay, let's see what will happen. Okay, so let me build the code with this change. Okay, now I'm going to run it. Okay, so it blinks as yellow. Okay, yellow on and yellow off. Okay, so basically in order for you to blink yellow on, yellow off, which means that both of them are running concurrently, correct? So it's quite similar to as if there was no mutex at all. Okay, if you remember the earlier lab. All right, and why is this happening? Okay, so this concept is very important. Many students have this thinking that, okay, I have declared this mutex to control the LED. So in the red LED thread, since I acquire and release, I have control of the LED. And in the green, there is no acquire and release, so I cannot get the LED. Okay, and why is this concept wrong? Because the idea that the mutex is tied to the LED is only in your head. Okay, I repeat that. The idea that the mutex is tied to the LED or tied to the motor or tied to anything is only in the programmer's head. Only you know why you created the mutex. The OS does not know why you created it, what is the purpose of the mutex. Okay, so when you created this mutex, okay, you had the idea in your mind that I'm going to use it to control the behavior of the LED. Okay, that means it is your responsibility to ensure that whenever I'm going to control this LED, I must acquire it, I must release. All right. So if you do not follow your own rules, then the OS cannot override that for you. It cannot tell you it's wrong. Okay, because the OS does not know why you created the mutex. Okay, it just follows the rule that, okay, if there's a mutex, if you say acquire, if it is available, you get it, you can proceed. If you say acquire and it's not available, you become blocked. So it follows the OS rules. It does not know what is your intention for the mutex. Okay, so this concept is must be very clear. All right, and why is this important is because in a project setting like this, you may develop some part of your code, your friend may develop some part of the code. All right, and you may have agreement. Okay, we will use a mutex to control this. All right, but you follow the rules, your friend does not follow the rules, and everything goes wrong. Okay, so you have to make sure that if you say I've created a mutex and the concept and the main reason for this mutex is to control the LED behavior, then it is the programmer's responsibility to ensure that every time I want to control this shared resource, in this case the LED, I must acquire and I must release. Okay, the OS does not know, it's not able to catch this kind of things. It's only the programmer who knows why he created this mutex. Okay, so this concept is very important. Okay, so just make sure that, okay, when you all are sharing and dividing the work among yourself, when you say that I have a mutex for this reason, I have a semaphore for this reason, everybody who is supposed to use that mutex or use that semaphore follows the rules exactly the same way. Okay, if one person doesn't follow the rules, okay, then things will go wrong. Okay, so that is the important thing that I wanted to emphasize, okay, before we go on to semaphores. Okay, so let's move on to the semaphores. Okay, so a semaphore is quite similar. Okay, the concept is quite similar to Mutex, alright, except that instead of thinking of it as a single token, okay, in Mutex we say it is a single lock and key concept, alright, but in Semaphore we say that it is a number of resources, okay, and in order for you to access any particular resource, you must first acquire a token, okay, and once you finish with using the resource, you return the token. Okay, and this allows resources to be allocated to different threads or different tasks depending on when they need to use it. Okay, so take for example, you have your microcontroller, all right, and maybe I have a single ADC channel. Okay, but I have multiple inputs, okay, that need to be where I need to perform the A to D operation. Okay, so or maybe you can say two A to D. Okay, so you share among a few different external peripherals who want to do A to D conversion. Now, which thread gets to use the ADC? All right, so you can say that, okay, this ADC, these two ADC module will be controlled, or this resource allocation will be controlled using Semaphore. So if I want to use a to D module, all right, one of the thread want to use a to D module, I must acquire a Semaphore. Okay, then when I try to acquire the Semaphore, if the ADC module is available, okay, then one of it will go to one of the thread. Then I can perform the A to D operation for one of the peripherals. Okay, then if while I'm using one of the ADC modules, okay, so this is maybe thread 1, then another thread say, hey, I also need to do A to D operation, correct? Then I can allocate another ADC module to another thread, correct? Then I can do for another peripheral. Okay, and along the way, another thread comes in, T3, and says, hey, I also want to do A to D operation. But then there are no more ADC modules left. So what will happen, this T3 will have to go to a block state. Okay, until one of the ADC modules gets freed up. Okay, and how do we know ADC modules gets freed up? That means the task which is holding on to this semaphore must release the semaphore. Okay, so again, you can see the concept is the OS is a set of rules. Okay, it gives us a framework with a set of rules on how different tasks can behave. How we use these ADC, I mean, these OS-based tools is up to us. Correct? You can say, hey, why must I use semaphore? Alright, I can just use a flag. I can use a global variable. I can, yes, you can use a lot of different ways of doing it. Correct? But if you have an OS, all right, it makes sense to make use of the OS-based tools to help you manage the multi-threaded environment. All right, so the whole idea is, if I use a semaphore to do this kind of resource sharing, I can ensure that if a task wants to do A to D operation but cannot do it because it is not available, I don't need to waste time. Correct? I can go to a block state, and when the ADC gets freed up, the OS will automatically unblock me, and I can proceed with what I want to do. Correct? So the OS can help you manage all this kind of transitioning between when a task can carry on, when the task will go to block state, and so on. All right. So the whole idea is the OS is giving you a lot of different tools. All right. It's up to us to make sure we use these tools correctly to manage, okay, the objectives or what you want to achieve. Okay. So let's look further. All right. So to get this semaphore or get this token, all right, there are different terminologies that you may come across. One common terminology that you will see in most reference books is P and V. Okay, so P is basically similar to OS SAM take. Okay, so again, OS SAM take, some books will say OS SAM take, some will say OS SAM acquire. Okay, but they all mean the same thing. Okay, V is after you finish, you release. So it's similar to saying, okay, OS SAM release, okay, or OS SAM give, and so on. Okay, so there are different terminologies that different OS may use, but they have the same idea. Take and give, acquire and release, and so on. Okay, so the whole idea is when I want to take a semaphore, I check whether the value is greater than 0. Okay, because like we said earlier, it is a number of tokens. It is not a single token. You can declare it as a single token also, all right, and it will still work the same way, or you can declare it as multiple tokens. All right, so in this case, I can say that I have a single ADC, and then my token count is 1. All right, so at any point of time, only one task can make use of the ADC module. Okay, so as long as when I try to take it, the value is greater than 0 means I can take it. Once I take it, I will decrement the value, okay, and I will be able to carry on. Okay, if for some reason I want it but it's not available, okay, so like for example here, when T3 comes along and it says I want to do A to D operation but it is not available, okay, then what will happen is you will move it to a block state. Okay, and of course whichever task that has currently acquired the semaphore, okay, once it is done with it, it will release the semaphore, okay, when call this function, and it will increment the value of semaphore by 1. Okay, at the same time, if there was a task that was currently blocked and waiting for the semaphore to be available, then that task will get unblocked and will be able to transition to the ready state. Okay, so that is basically the semtake and semgive operation. So let's look at an example here. Okay, so let's assume that currently I have 3 resources. Okay, so as it goes to 3, which is the total number of resources. Okay, and a task comes in and acquires a resource. So P is to take. Right? P is to take a resource. So I take a resource. So from 3 becomes 2. Okay, then I take again, becomes 1, and I give back after that. Okay, so the task that initially took the resource is done with the resource, so it gives back, so the value becomes 2. Okay, increments again, and then another task comes in, takes the resource, again it decrements. Another task comes in, takes the resource, and now it becomes 0. Okay, so currently initially there were 3 resources. Now all 3 resources have been taken up. Okay, and now another process or another task comes in and says I want to take the semaphore, but it is not available. Correct, it is 0. So in this case, that task will get blocked. Okay, and we put in the queue. Okay, so you will join the queue. This queue is basically the queue of tasks that are waiting for a semaphore to be released. Okay, they are waiting. Then another task comes in, and that task also say, hey, I also want this resource. Okay, but since there is no resource available, it also gets blocked and it gets put in the queue. Okay, so X is in the queue, Y is in the queue. All right, then one of the tasks that was currently having the resource releases the resource. All right, and what happens? It unblocks process X. Okay, unblocks process X. So if you notice, okay, at this point of time, okay, compared to, let's say, okay, maybe, okay, if I compare this and this, let me see now. Okay, so okay, if you look at, for example, this to this, okay, previously it was 1, but when I release it became 2. Correct. So rightfully when you release, you increment the count. But in this case, you can see that when initially was 0, but when I increase, when I release the semaphore, it still stays as 0 because it automatically allocates it to the task that was waiting in the queue. Okay, so it does go to 1 momentarily, all right, but that is just to signal the OS that the semaphore has been released. So the task that was waiting in the queue automatically gets allocated as semaphore and the count goes back to 0. All right, so that's why the S value still stays at 0 and you unblock process X in the meantime. Okay, similarly, when another task releases, again, it momentarily goes to 1 to signal the OS that the resource has been released, but the task that was in the queue gets allocated and immediately it goes back to 0. But you unblock the process Y which was waiting in the queue. Okay, and then after that, when other tasks start releasing and there's nobody in the queue waiting for the resource, that is when the count will start to go up. Alright, so that is basically how the OS actually manages the semaphore usage. Okay, again, as I mentioned before, how we use the semaphore is up to us to decide. All right, I will show you in a while in the lab manual example how we can use it to synchronize or control certain aspects of task execution. Yeah, but okay, so the question is we can't use the semaphore to tell which ADC to use. That is correct. Okay, we can't allocate or assign it to any particular resource in a sense. Okay, like I said before, if you have, for example, two different ADC. Okay, so in the case, for example, okay, so as I say, I have two ADC module in my microcontroller. If I declare my semaphore, okay, and I put it initial count as 2 to manage both these ADCs, then it will treat both of these resources as the same, as being equal. Okay, so there's no differentiation between which ADC, ADC 0 or ADC 1 or anything like that. Okay, but if you have some specific need, okay, so for example, your microcontroller has an 8-bit ADC, okay, and at the same time has another 12-bit ADC. Okay, so if you have two different ADC and you want to manage them separately, then you use separate semaphores, okay, to manage them. So if you're using semaphores in general, they will treat the resources the same. Okay, so if I use, why not use a counter variable or so on? So yes, like I said, you can use a counter variable, you can do everything. But the idea is if you use a counter variable, okay, or use some other global flag, then what happens? You need to check it, correct? To know when it's available, when it's not available. Okay, if I use the OS, that part is handled for me by the OS, correct? Because the moment it's not available, I'll be blocked. When it becomes available, I will automatically be unblocked and be able to carry on. Okay, so is Semaphore and Mutex the same? Some similarity, but there are differences. Okay, I will show you in a while. Okay, what are the differences? Okay, so there are some significant differences, even though in some cases you may think of using them to be the same. Okay, so in to create a semaphore, you need to call this function OS semaphore new. Okay, you can put in the maximum count. So this is the total number of resources. And what is the initial count? Okay, so initial count is in, do I start from the full, or is it currently I can only start with current value of 1 or 0 up to me? Okay, so it all depends on how you want to use the semaphore. Okay, so that is the OS semaphore new. Then the acquire and release is basically to get the semaphore and to release the semaphore. Okay, so this is basically the LED red thread and LED green thread. Okay, okay, so let me show you this in the code. Okay, and we can see what happens. Okay, and at the same time we will review the concepts of the lab as well. Okay, so let me share the code with you. Okay, so this is the code just now we saw. So in this case, we are creating a new semaphore. Okay, so maximum count is 1, initial value is 1. Okay, so if you look back at the parameters, the first one is the maximum count, the second one is the initial count. Okay, so I'm going to make sure that the maximum count and initial count are both 1 and 1. Okay, and after that I create both the threads. Okay, so as before, both the threads will run. Okay, and in this case, your LED red thread will acquire the semaphore, correct? And since the initial count is 1, what will happen? It will decrement and become 0, correct? Once you get the semaphore, and then I'll control the red LED. And of course, due to OS delay or due to context switch, I will come over to LED red thread. Okay, and when LED red thread try to say OS semaphore acquire, what will happen? It will see that the current semaphore value is 0. correct? So when the current semaphore value is 0, what happen is you will go to a block state, correct? You will wait until the semaphore gets released, all right, and that will happen over here, okay, when the red thread releases. And since the green thread was already waiting for it, correct, it was already blocked and waiting for it, the moment the red thread releases, the OS will automatically allocate it to the green thread. So the next time around, the green thread will run. Okay, so it will be quite similar, okay, to what we saw with the mutex behavior as well. Okay, now, so let me run this code first. Okay, so if I run the code, you will see that the behavior is the same. The red LED blinks first, and then the green LED blinks, correct, one at a time because of the semaphore. So in this situation, the semaphore and the mutex that we saw previously seem to have the same behavior. Okay, nothing different for that. Okay, now let's look at the lab manual. Okay, and in the lab manual that you have for lab 8, okay, you are going to look at this concept of how to use semaphore to trigger tasks. Okay, until now, if you notice, when the program runs, okay, the moment you load the program, the threads just start running, correct? The threads just start running. But in some cases, you want to trigger the task, correct? And I send a data or some event happen, then the task will run. Just like, for example, like when you control the robot, okay, when you receive a particular data that says that I want the motor to move, then only I want the motor to move, correct? Now, how are you doing it right now? You could have been doing it currently using some global variable, okay, that you set in your interrupt, and then you read from it, okay, in your thread, okay. But if you have a global variable, okay, where you do this kind of management, then what happens is, in your thread, when you're reading this global variable, if that variable is not set to the value you want, okay, then you may end up wasting time, correct? So what you ideally want to do is, if I do not get the data that I want, or I'm not supposed to run at the moment, I go to a block state, correct, or I go to a waiting state until that data or that event happens, correct? So there are a few different ways we're going to look at today how to make this happen. So in this lab 8, okay, what we're going to look at is semaphores to trigger tasks. Okay, what we're going to do is we're going to use the interrupt push button from your previous lab. Okay, so let's look at that. Let me connect up the switch first. All right, so what we're going to do is I'm going to connect up the switch. Okay, so the switch is connected to, okay, so I'm connected up the switch, okay, based on how we did before. Okay, so the same switch as before. And so basically what's going to happen is, in your code, okay, in your lab manual, what we want to do is we want to make the push button trigger the task. Okay, we want the push button to trigger the task. Okay, so by default, what I want is, the moment the system starts up, okay, I do not want any LED to blink. All right, but when I press a button, then I want the red LED to blink. Then when I press again, I want the green LED to blink, and so on. Okay, so let's do the first thing first. If I do not want any task to be running after the system startup, what is the first thing I can do? Okay, using semaphores. Any idea? With this current code that I have, I do not want any of the thread to run when the system starts up. Okay, yeah, set the count to 0. Okay, that means the initial count here from 1 I change to 0. Okay, why? Because if I change this initial count to 0, the moment the thread run, it try to acquire, it go to a block state. Okay, so if you were to look at the timing diagram, okay, so since I have the red thread, so I have the LED red thread, okay, and the LED green thread. Okay, so if my initial semaphore value, Okay, my initial semaphore value is 0. Okay, when my LED red thread runs and it says semaphore acquire, what happen? It will go to a block state. Okay, so once it goes to a block state, the LED green thread will be able to run. Correct. So initially it was ready. Okay, and then it will transition to run. Okay, but the moment it transition to run, the first thing it do, it also asks for semaphore acquire. Okay, and since it is again still 0, it will go to a block state. So both the tasks will go to a block state. All right, and what I want is I have a push button. Okay, the push button is basically tied to my IRQ handler. Okay, so when I press the push button, I will trigger the interrupt handler. Okay, that we already have done in the earlier lab. And inside the interrupt handler, what I can do is I can say sem release. Okay, so when I do a sem release in the interrupt handler, what will happen? Whichever task that was first in the queue. So you can see that if I were to draw the queue, okay, if I will draw the queue, first it was red thread and then the green thread. Okay, and then both of them are blocked, correct? So when I do a sem release, the first person to be released is the red. So the red will blink, correct? But the moment the red blinks, okay, it releases the semaphore, okay, and after that, what happens? The green thread, okay, will still be waiting, correct? The green thread will still be waiting for the next semaphore. Okay, so the green thread will wait until the next semaphore has been released. Okay, so let's look at that, okay, and see how to do that in the code. Okay, so if you look at it, basically the LED red thread and LED green thread, I also need to do one thing. I also need to make sure I do not release the semaphore over here. Okay, so I just acquire and then I wait until the release is done by the IRQ handler. So in the IRQ handler, I will do the OS semaphore release. Okay, and inside my LED red thread, okay, I just do the acquire. Okay, so let me bring up my camera here. Okay, so as you can see, when I run the code, there is no LED blinking. Correct, both the LEDs are off. Okay, if I press a button, okay, the red LED flash one time. If I press again, the green LED will flash. Okay, so every time I press the button, okay, the red LED flashes. And then the next time I press, the green LED flashes. So it is continuously toggling between red and green, all right, because at any point of time, okay, if you look at the code, okay, the LED threads are acquiring the semaphore, all right, but the only person who is releasing the semaphore is the interrupt handler. All right, so this actually gives you an idea, correct, of how you can trigger a task to start running after a particular event has happened, correct? So for example, you say, okay, after my motor has moved certain amount or my song has played a certain amount, then I want to light the LED or do something. All right, so a task could be blocked waiting for a semaphore, all right, and your other task can choose to release that semaphore at a particular time, correct? So this sort of gives you the idea of how to synchronize between tasks. Okay, so if for example you have T1, okay, and T2, okay, and of course in a multi-threaded environment, we know that at any point in time anything can happen, right? You can have context switch, you can have intra everything, but you can say that okay, at some point of time I want to wait, okay, for T1 to have completed some activity, so I want to wait. All right, so what I can do is over here I can say OS sem acquire and make sure that the semaphore's initial value is 0, and when task 1 has completed until a particular point, okay, which I'm waiting for, then I say OS sem release. Okay, then task 2 can unblock and then carry on. Alright, so of course it doesn't mean you immediately carry on. Correct? We know that what it does is it will transition the state from block to ready, and then depending on other factors, it will eventually transition to run. Alright, but in a sense, it gives you the idea of how you can synchronize the behavior between different tasks. Okay, using semaphores. Okay, so so that is what you will see in this lab. Okay, so if you can do it, okay, on your own. All right, basically you have your switch, you have the code, everything, and of course there's also a part where I ask you to integrate the UART code inside, okay, from your currently what you're doing. So currently you already have the UART interrupt already in place, okay, and you are able to trigger based on data coming in through the Bluetooth. All right, and what you can do is you can actually say that one of the tasks, for example, red LED or green LED, will be waiting for the semaphore. Okay, and then you release the semaphore based on that particular data that you receive to control the different LEDs. Okay, so that is basically the objective of Lab 8. Okay, now let's discuss another variation to this, okay, and see what happens. Okay. Okay, so now this whole thing that we saw, okay, if let's say, okay, let's just say that I decide to implement the same thing using Mutex, okay, because like I think most of us have the thinking that okay, Mutex and semaphore can be sort of interchanged, because if a Mutex value is 1, all right, it behaves very much like a semaphore. That means it's a single token. All right. Okay, so if let's say now I replace my semaphores with Mutex. Okay, so let me show you the code. Okay, let's see what happened. Okay, so this is the code. So basically what I've done is I have changed the entire semaphore usage to Mutex usage. So instead of creating a semaphore, we create a Mutex. Okay, and in this case, I acquire the Mutex here. All right, in both the LED threads, and the Mutex release is done over here in the IRQ handler. Okay, so of course, Mutex initial value is 1, correct? I mean, initially it is considered available the moment you create it, correct? So definitely when you run, okay, the LED red thread will run first, correct? You'll be able to acquire the Mutex, but of course it does not release the Mutex, okay? But I'm able to release the Mutex here in the IRQ handler. Okay, so now with this code, okay, same as before. Only thing is, like I said, the Mutex initial value is 1, right? That means it's available. So okay, so what do you think will happen if I were to run this code? Would it be the similar behavior as before, where I say that the controlling the switch based on the LED? Okay, so if I run the code, like I said, the red LED will blink 1 time, all right, because the mutex is created. So once the mutex is created, it's available, so the LED red thread will run. All right, so if I press the switch, okay, nothing happens. Okay, if I press the switch, nothing happens. Okay, and why nothing happens is you can look back at the documentation. Okay, if you look at OS mutex release, okay, it says that it cannot be called from the interrupt service routine. Okay, it cannot be called from the interrupt service routine. Okay, so again, this is another important thing that I wanted to show you, that again your compiler does not catch this kind of misuse of OS kernel calls. All right, so it does not flag off as a compiler error that you put a mutex release in the ISR. Okay, because that is a programming error. Okay, so as far as the compiler is concerned, it will not be able to catch this kind of thing. So you must be careful of what is allowed, what is not allowed by looking at the documentation. All right, if not, you may spend a lot of time trying to debug and think why it is wrong, but it's not. Okay, so the reason why you do not have mutex release in the OS is the same thing. If you look at OS mutex acquire, it is also not allowed. Okay, and the reason why they enforce this is because if you do not, because in most cases, okay, unless you put the timeout to be 0, okay, and then you can carry on, correct? But if let's say the programmer go and puts OS wait forever in a interrupt service routine, then you end up being stuck in interrupt forever, correct? If the mutex is not available. Okay, so that is why they do not allow certain things, all right, but it does not flag off as error in compile. Okay, but they enforce certain things. So even though in your code you have it, when you compile it, there is no error, there is no warning, all right, but it will not work. It will actually return as an error. Okay, so in this case, okay, if I were to use the capture the return value, okay, you can try this on your own. If I use the my status, okay, OS status return value to capture the return, okay, you will be able to see that the return value is actually OS error ISR. Okay, then you know that something went wrong. All right, so it's always a good practice to do this. Okay, put a my status here. Okay, and this my status is of course your OS status. All right, so this actually helps you to capture the return value so you know whether it returned an error, and then from there you can look at documentation and know what kind of error it was. All right, so these are some of the things that you need to be careful about, okay, when you're using the OS. Okay, so what the compiler can catch, what the compiler cannot catch. All right, so again, take note of these kind of things. All right, and if things don't work, okay, with the OS implementation, try to always capture the return value and see if that return status error or status message gives you some information on what could be the possible reason why it's not working. Okay, so that is basically the OS semaphore usage, and of course, what you're going to see in your lab. All right, so in this lab, okay, and what you'll be doing is you can see that, okay, now with semaphore, I have this idea. I can signal a thread. Correct, I can signal a thread. Okay, so like what I drew here, my push button, okay, can be used to release a semaphore, and then my LED red and LED green can, or one of the threads can use that to sort of get unblocked and then carry on. Okay, but of course, what is still missing is what? It is still missing. One important thing is how to send data together with unblocking the task. All right, that means instead of just saying semaphore release, when I say semaphore release, okay, whichever task which was blocked, all right, will get unblocked. All right, but if I want to unblock the task, but at the same time send some data together, then I need to use something else. All right, so semaphores are good, all right, when you just want to synchronize some behavior of tasks. But if you want data transfer to also take place at the same time, then you need to use something else, all right, called message queues. All right, so in the next lecture, okay, after the break, we're going to be looking at flags, events, and message queues. All right, where we're going to look at other ways of synchronizing first, and then we're going to look at message queues. All right, so we're going to go for a break now. When we come back at 10 o'clock, okay, I'm going to go to the slides 14. Okay, the lecture 13 slides is basically just a review of the RTS concepts. Okay, I will leave that to next week. Okay, we go to lecture 14 first. so that I'll cover these important concepts on the flags, events, and message queues, and then you understand how to create your architecture for the project. Okay, so we'll go for a break now, and I will see you back here in 10 minutes time. Okay, so so just now there was a question on what happens when you release and you already hit the maximum count. Okay, so I went to check on it again. All right, so just now I told you that the task that is releasing it can get blocked. All right, but it seems to be not the same for RTX. Okay, so that was for a different OS that we were teaching in the past. All right, for RTX, the behavior is such that, okay, if you look here, it will return an error. That means basically uh, the function will return an error, so it will not do anything. Okay, it will not put it to a block state or anything, but it will just return as an error code if you try to call OS Semaphore release while you are already at the maximum count. Okay, but it will still be able to carry on. Okay, so that is basically what will happen if you try to keep on releasing the semaphore, okay, and you hit the maximum count of what you have already initialized the semaphore when you call OS Semaphore new. Okay, so that is a clarification on that. The next thing is, okay, so there are a few more slides that I haven't gone through on the Mutex and Semaphore. So let me finish up that first. All right, so what is the similarity or difference? Okay, as we saw just now, one of the things is Mutex, as you saw, we cannot call or use it, okay, in the context of ISR, whereas Semaphore you can do it. All right. So certain things you are allowed to do with semaphores, okay, but you're not allowed to do with Mutex. All right, so that is to enforce certain sort of behavior on how you're supposed to use the OS. All right. Another thing is for semaphores, when you create a semaphore, you can initialize them to 0, okay, which means that you don't have any resources at the moment. It's possible, okay. So like what we did just now, we initialize to 0 and then we allow the ISR to increment. All right, so the semaphore can be triggered, can be used as a way of signaling between tasks or task and ISR, okay, to sort of synchronize their behavior. The idea of Mutex is to ensure that you protect a shared resource. Okay, so in some cases, yes, you can say that, hey, I can use Mutex for this, I can use Semaphore for this, and both of them seem to have the same behavior. All right, but again, the idea behind Mutex and the idea behind Semaphore is a bit different. Semaphores, the concept is you manage some resources which are shared among different tasks. You can have one resource, you can have multiple resources. Mutex is again to protect access to a shared resource. Okay, so you make sure that if I have a shared resource, like an LED or an ADC module, and I want to make sure I have exclusive access to it, then I can lock the access and then release the access after that. Okay, so in a sense, if I declare a semaphore with a count of 1, then we call it a binary semaphore. Then the behavior is almost the same. But one of the important things is this: priority inheritance. Okay, so in the tutorial question, okay, you would have gone through, priority inheritance allows a lower priority task to temporarily inherit the priority of a higher priority task, okay, whenever there is a priority inversion situation happening. Okay, so in your tutorial, one of the questions was that. Okay, so you can see that in Mutex, you have this priority inheritance built in, okay, which is important, okay, to prevent a priority inversion problem. All right, so that is one of the differences between Mutex and Semaphore. Okay, Semaphores do not have priority inheritance. Okay, Mutex has this. Okay, so that's why it's important to use them in the correct context. Okay, where you have a resource that is shared among different tasks, and you want to make sure that you have priority inheritance, then you use Mutex. if you are intending to synchronize the behavior or flow of different tasks, then you use semaphores. Okay, and like what one of you mentioned, we discussed earlier, it does not differentiate between resources. That means if I create a semaphore with a count of 2 or 3 and I say this is for all my timer blocks, all for my ADC blocks, then it treats all of them as identical. All right, if I want to differentiate them, then I need to have separate semaphores for them. All right, so it does not differentiate them, it treats them as being identical. Okay, so another possible situation you can occur, all right, with this kind of mutex behavior is deadlock. Okay, where everybody is waiting for each other and nobody wants to release their resource. Okay, so for example here, okay, process 1 and process 2 both require resource A and resource B. Okay, so maybe I draw the timeline here. Okay, so let me draw it over here. So I have process A and process B. Okay, so this is the timeline. Okay, so let's say along here, okay, both process A and process B, both of them require resource 1 and resource 2. Okay, so you have two processes and both of them require two different resources, R1 and R2. Okay, so let's assume that process A runs first. Okay, and at this point of time here, I acquire resource 1. That means I get resource 1. Okay, and let's assume that something happens, all right, some context switch happens, and then I go over to process B, all right, and while process B is running, okay, so all the while I was ready, okay, then over here I start to run, and then at this point of time I get hold of resource 2. Okay, and then after that I carry on running. Okay, and then again there is some context switch happening, and then process 1 is able to resume. And when process 1 resumes, let's assume at here I try to get resource 2. What will happen? It is not available, correct? So I'll go to a block state. Okay, so when I go to a block state, okay, so maybe the other tasks, okay, whatever else happened doesn't matter. Eventually, at some point of time, okay, I will be able to transition back to process B, and process B is running, and process B runs, and also at some point of time asks for resource 1, and resource 1 is held by process A, and then it will also get blocked. Okay, so you can see that in a situation like this, okay, both processes require two shared resources, but they took the other one, correct, in different order. So what will happen is your process B also gets blocked, the process A also gets blocked. Okay, so this is basically what happens when you have this is basically what you call a deadlock situation, where the tasks are holding on to resources that the other person wants, and both of them are also happen to be blocked, so they cannot release what they have also. Okay, so this is basically a deadlock situation, and usually if you reach this kind of situation, your whole system might hang, okay, and it's become unresponsive and so on. So this is of course a design issue, right? The person who is writing the software, okay, must take this into consideration. Okay, that if I have shared resources, how do I manage them? Okay, so of course, again, these are things that some compilers, okay, along the way have been able to advance to a stage where they are able to analyze the code and give you some idea that, hey, this could be happening. Okay, but again, it may not be across the board. Okay, so it is still up to the programmer's responsibility to ensure that this does not happen. Okay, and one of the ways in which you can enforce or prevent this from happening is, okay, you acquire shared resources in the same order. Okay, that means if process A and process B both require resource 1 and resource 2, then I enforce that everybody must take resource 1 first, then resource 2. Okay, then this problem wouldn't come, because then when process B runs, instead of taking resource 2, it will try to take resource 1, and then it will straight away get blocked because process A already has resource 1. Correct? So it ensures that whoever grabs that first resource will be able to carry on and finish up before releasing the resources. All right, so this is one way, all right, for where the programmer can ensure that if I have this kind of situation where multiple tasks have shared resources, everybody acquires them in the same order, that can prevent a deadlock situation. Okay, so again, it is up to the programmer's responsibility to check your code, check your shared resources, and ensure these kind of things are avoided. All right, again, some compilers can catch it right now, okay, but again, it may not be all the time. Okay, so that is basically the last part of this chapter here on deadlock. Okay, so with that, we conclude the Mutex and Semaphore topic. So let me go on to the next one on messaging and synchronization. Okay, so in messaging and synchronizing, we are going to look at first 2 other ways of synchronizing tasks. Okay, so we saw one way, which is a semaphore. Now I'm going to introduce you to 2 other ways which are quite similar, and then we're going to go on to the message queues. Okay, so again, why is this important? Because in a OS system, you need to have inter-task communication. All right, because there's always a lot of data to be shared, a lot of events that will trigger one task to do another task, and so on. All right, so we need to, as much as possible, maximize the use of whatever the OS is giving us. All right, so as much as possible, try to see what the OS has that can help me fulfill this task. Don't declare like 2000 global variables and say, okay, all my problems solved. Okay, so that is not the right way of doing things. All right, so when you have an OS, okay, you should try your best to make use of what the OS has. Okay, again, right now you may say, okay, you solve my problem, it's fine, it's okay, but you know, as you graduate, you join the workforce, you're going to do your own startup and so on, you want to make sure you do things the right way. All right, if not, you have an OS, all right, but then you are not fully utilizing the OS because you are still thinking in the single-threaded mode of solving problems. All right. So in this chapter, we're going to look at these things. So we have looked at Mutex and Semaphore. All right, and now we're going to look at flags, events, and mailbox. Okay, so mailbox, some of them call it message queue. They are quite similar in most implementation. All right, and both of them, what they do is they are able to provide some form of synchronization, and mailbox and message queue also provides data communication. Okay, that means you are able to send data while synchronizing at the same time. Okay, so the first thing is flags. Okay, so the good part about flags is they are not created. You do not need to explicitly create them. They are automatically created when you create a new thread. Okay, so when you create a new thread, you are at the same time creating thread flags. All right, and each thread has 31 thread flags from 0, okay, all the way to 30. 31 thread flags that are already available the moment you create a thread. Okay, but in order for you to access this, you need to know the thread ID. Okay, so until now, when we call OS thread new, we were just interested in the thread name. Okay, but now we want to capture the return, and the return is actually the thread ID. Okay, and why this thread ID is important is because we want to use the thread flag. So we need to know which thread we are talking about. Okay, so that is the thing that we need to now take note whenever you are creating a new thread. Okay, so with thread flags, what you can do is you can set and you can wait. Okay, so I can set the flags of any thread that I like. All I need to know is I need to know which thread I'm referring to. All right, and a particular thread can also wait for its flags to be set. Okay, you can wait for its flags to be set, and then you can decide what action to take after that. All right, so let me show you an example here. So in this case, I have two threads, LED on and LED off. Okay, so this information, TID LED off, this information is obtained when I call OS thread new. Okay, so when I call OS thread new, okay, the return is this, the ID. All right, so when I capture the ID, all right, I can use this ID and any thread can set the flags of any other thread. All right, so over here, what is happening is in the LED on thread, I am setting the flag for the LED off thread. Okay, so this LED off thread, okay, like I said, when you create the thread, automatically you have 30 flags. Okay, 0 to 31 flags, 0 to 30. Okay, and what the LED on thread is doing is it is setting the flag 1. That means this particular flag, I'm setting it to 1. All right, and then I'm calling an OS delay of 2000. So initially I on, so that is this going up here. All right, and after that, what do? I say delay for 2000. That means 2000 ticks later, I come back here. And I come back here. Okay, so the first bit is reserved. That is the current design of the RTX. All right, there is no particular reason that I know of, but probably they've reserved it, okay, for some future expansion or future use. Okay, but for now we have 31 flags that we can use. Okay, so you can see here that when I set the flags, okay, I wait for 2000, OS delay of 2000, and what is happening here? In LED off, okay, so once I call OS delay, what happened? I'll go to a block state. Right, I go to a block state for 2000 seconds. Then what will happen is, when I go to a block state, okay, let's assume there's no other thread in the system, so I'll come to LED off. Okay, so when LED off runs, it is actually going to wait for the flag to be set. And which flag? The flag in bit position 0. Okay, so when this flag is set, all right, again you can see that it waits. OS flags wait any and OS wait forever. So what are these two options? If you look at these two options, OS wait any means I wait for any of the flags to be set. Okay, so in the next example you'll see this a bit more, but timeout, okay, is basically wait forever. That means I will wait forever. That means I'll wait until that particular flag is set. All right, and once that flag is set, then I'm able to unblock, okay, and carry on running. So I will delay for 500 and then I'll call LED off. So I wait for 500 and call LED off. And then what will happen? I will go back here, right? It's a loop. And then what I'll do, I'll wait again. But since I've already captured the flag from the first time that I run, I need to wait for somebody else to set the flag one more time. Correct? And when will that happen? When this task finishes the OS delay and comes back again. Correct? So that was 2000 units of time later. Correct? So then I come back and I do again. Okay, so this signal that you see happening is basically through flags. Okay, through flags. Okay, can I do the same thing with semaphores? Yes, you can. All right. So, like I said earlier, you have different tools. Okay, and you can decide which tool you want to use. Okay, depending on what you want to achieve. Okay, so of course, one of the advantage of this is this OS flags wait any. Now let's look at the next example and you see why. In this example, you can see that for thread 3, I've used this option called OS flags wait all. All right, which means that I want to wait for the flags in bit 0 and bit 1 to be both 1. Okay, because I'm waiting for 3. Bit 0, bit 1, both to become 1. So I must wait for all the flags to be set. Right, so this is one way where I say, okay, task 1 runs until a certain point. Okay, so task 1 must run until a certain point, task 2 run until some other point, then task 3 must be able to start running. Okay, so at this point of time, I set a flag. Okay, then this point of time, set another flag. Then when both of them are set, then task 3 can start running. All right, so I can have another way of synchronization where multiple tasks are able to have achieved some level of completion, then my next task can start running. All right, so if you see here, task 1 sets bit 0. Task 2 sets bit 1. So this is bit 0, this is bit 1. And then over here, I wait for both bit 0 and bit 1 to be set. Then I can carry on. Okay, so if you think about it, yes, I can do the same thing with semaphores also. All right, I can create 2 separate semaphores. Okay, here I release one semaphore, here I release another semaphore, here I wait for 2 semaphores. All right, so it is possible to do the same thing with semaphore. It is possible to do the same thing with thread flags also. Okay, which one you want to use is again up to you. Okay, but again, these are all different ways of achieving some way in which you want multiple threads to sort of synchronize or communicate with each other in terms of when they should start executing. Okay, so that is thread flags. Okay, and like I said, thread flags are already created when you create a new thread. Only thing you need to know is the task ID. Okay, so you need to know the particular task ID. Okay, to make sure that you are setting the flags for that particular task that you are referring to. Okay, now the next thing is events. Events are exactly the same as flags. Yeah, exactly the same. Only thing is they are not tied to any particular task. They are not tied to any particular task. So you need to explicitly create them yourself. Okay, so I can call OS event flags new to create a new set of event flags. All right, and then use them exactly the same way I was using the flags. Okay, so I can do event flag set, event flags wait just as before. Okay, so if I look at this example here, it's the exact same thing. Only difference is I need to make sure I call OS events flags new somewhere in my task earlier on, and then I create. So just like how you create a new semaphore, you create a new mutex, you can create a new event flags. All right, and then you just can reference this event flag from any other task. So in this case, LED on sets the event flag. Okay, here, and in LED off, I wait for the LED flag bit position 0 to be set. Okay, so you can see that it is again another alternative. Okay, so the task, the same task can be triggered by event flag, can be triggered by thread flag. Okay, the behavior is the same, it's just whether I want to use a thread flag or event flag. Okay, the advantage of thread flag is you already have it built in into the thread itself. Event flag, you must create it separately. Okay, so that is the main difference. And of course, in this case, if you have a situation where you want a common flag to be shared by a few different tasks, then you can use event flag. Okay, if one task is going right to another task flag, then you can use thread flag. Okay, but either way, you can always think of a lot of different ways of working around and interchanging their usage. Okay, so again, it all depends on how you want to use it and what you want to achieve with this. Okay, so the last one is message queues. Okay, and like I said, why is message queues very important is it allows a way of communicating, all right, where you not only synchronize, but you also send data. Okay, so you are able to communicate by synchronizing at the same time sending data. All right, and you can have a thread with sending data, okay, and receiving, and you can also use them in the context of threads or interrupts as well. Okay, so let's look at this. So in this message queue, what you can do is you can call OS message queue new to create a new message. Okay, and you can specify the size of the message, how many messages, all right, and any particular attributes that you want to change. Okay, and then one of the tasks can put a message. So if I create a message queue, okay, I can say task 1 will call message queue to put a message inside. Okay, so if many tasks can call the same message queue and put messages inside, all right, and once you want to read from it, you call OS message queue get. Okay, now the parameter timeout here, as you can see, specifies how long the system waits to retrieve the message. Okay, that means if I specify, okay, that I wait forever, which means the thread that is calling this function can be put to the block state. All right, so this allows you to synchronize. Okay, so for example, I have a motor task. Okay, your motor task cannot move until you get the first message. All right, so you have your ISR. Okay, and you can say your ISR will call OS message put. Okay, so when I put the message, all right, this motor task can be waiting on OS message get. Okay, so if there is no message, that means nobody has sent me any information yet. I will go to a block state. Okay, until the ISR has processed the information and sends me a message. Okay, same thing, your LED task. So all of these tasks, okay, your buzzer task, all of your tasks can be waiting, okay, for the message to come in first. Okay, so message get. So all of them are waiting. Okay, and who sends the message? Your ISR. And your ISR gets the data from your phone. Okay, so the moment the data comes in, your ISR processes it and decides, okay, based on the data packet that I receive, okay, this first 2 bits tell me this is a motor control message. Okay, so if it's a motor control message, what do? I need to control or move the motor forward. At the same time, I need to blink the LED. Okay, so I can send one message to the motor task, then I can send another message to the LED task. All right, so that both of them will wake up and both of them will run concurrently. Okay, so one way in which you can design architecture is all your tasks can be in a waiting state. Okay, so they're basically blocked, waiting for message to be received. All right, and your ISR decodes the message from your phone and decides, okay, which are the tasks I need to activate now. Do I need to activate the buzzer task? Do I need to activate the LED task or the motor task? And send each of these tasks appropriate messages. Okay, and all of them will then be able to get unblocked and they will all run concurrently and fulfill the objective. Okay, so the first thing is, okay, let's look at how we can use this, okay, for the project. So in my case here, I'm going to declare a message structure where I have a data packet where you have 8-bit command, 8-bit data. Again, this is only an example. If I think some of you asked me before in the lab, how big should your packet be? And it's all up to you. Okay, it's up to you to define. If I can put all my information that I want within 8 bits, then you just send 1 byte at a time. All right, that means your phone sends 1 byte data and your controller board decodes 1 byte data and then sends it out. Correct? How you want to divide this 1 byte data is up to you. Correct? So you can say 2 bits for motor, 2 bits for LED, 2 bits for buzzer or something like that. Up to you. Okay, if you think you want more bits, then you can make it into 2 byte data or 4 byte data, all up to you. Right? And what I'm going to do is, in this case, I create new message queue IDs. Okay, so when you create a new message, okay, when you call OS message queue new, okay, you need to capture this ID, the return value, because you're going to be using this later on. Okay, you're going to be using this later on. So that is why I create the OS message queue ID over here. Okay, and then what I do is I create 3 new message queues. Okay, so in this case, why I create 3 new message queues is because I have 3 separate tasks for each LED control, correct? If you just say I have only one RGB LED task, all right, one RGB LED task, then I need to just create one message queue, okay? Because in this case, I have one task that will decode the data and decide which of the RGB I want. But in my example, I have 3 separate tasks, so I have 3 message queues. Okay, so I create 3 message queues, and then I declare how I want the data structure to be. Okay, so in this case, I declare the first byte as command and the second byte as data. So I just keep it simple. All right, where 01 is the LED and the 01 for the data is blink. Okay, so in this case, you can see that when I put my data here, all right, when I call OS message queue put over here, what happens is each time the task that is waiting for the message will get unblocked. All right, so if I look at the LED thread here, for example, the first thing that you see in all the 3 tasks is I call OS message queue get. Okay, which means what? That means when my system starts up, all of them are waiting to receive a message, and if there is no message, all of them will go to a block state. Okay, all of them will go to a block state. All right, until they receive a message. So when I send a message, for example, this first line here, when I send a message to the red message queue, what will happen? This task will receive the message, so it will unblock. So when it unblocks, it will then go and decode the data and then decide what it wants to do. But the moment it does it, what happens? It goes back and waits for the next message queue. Correct? So every time I send a command, it does something and then it goes back and waits for the next message command. Right? So that is basically what happened. So you will see there is red, green, blue, white, and so on. Okay, why white? Because over here, I will have all 3 LEDs receiving messages concurrently. So this is what I mentioned just now. You can send out multiple messages to different message queues at the same time. And if all 3 are waiting, all 3, how many of them will get unblocked and all of them can run concurrently. So when I do this, okay, all the 3 tasks will receive the message and all 3 will unblock and be able to run concurrently. Okay, so you'll be able to see that after red, green, and blue, it will be white. Okay, now let me show you the code. Okay, in the lab manual first. Okay, so in the lab, you are going to do this first. Okay, and then you're going to modify this a bit more. Okay, so let me bring it up. Okay, so I will skip on the first 2, which is on the threads and events. Okay, and I'll come straight to the message queues. Okay, so the threads and events, you can try it out on your own. It's similar to what I explained in the lecture just now. Okay, so for the message queues, okay, what we're going to do is we are going to keep the same structure, but except the data will have different formats. So previously it was just 01, which means you blink. Okay, but now I have 4 different types of data, which will decide the blinking rate. Okay, so there are 4 different blinking rates. Okay, so you can think of it as similar to, for example, how fast you want your motor to move, correct? Slow, medium, high, or very fast, or something like that. Okay, so it's the same thing, but of course, again, you do not need to split into 2 bytes. Okay, if you want to squeeze everything into a single byte, it's also fine. Okay, it's all up to you how you want to decide. Okay, in my example, I'm going to use a control thread. Okay, so let me bring it up here. Okay, so let me go through the code with you, so you understand what's happening. So this part is basically what you have done before. You have the 3 LED threads. Okay, I have created this control ID thread just to mimic the behavior of pressing the button on the phone. Alright, so rightfully, if you press the button on the phone, you send it, get to the interrupt and so on. But in this case, I create a control ID thread to simulate this behavior. Okay, and then I create the 3 message queues. Okay, and these 3 message queues are to make sure that I'm able to send data to the 3 different tasks. Okay, and at the same time synchronize them. Okay, so let's look at each task. Okay, so the control Okay, let me look at each task first. So for each task, okay, let's say LED blue thread. Okay, what I do is, as you can see, the first thing that I do is I call OS message queue get. Okay, and the objective of OS message queue get is to get a data coming into that particular message queue that was created for this task. Okay, and as you can see, I OS wait forever, which means that if there is no message coming in, I will be blocked. Okay, so I will not go past this line until a message has been received. Okay, the moment a message has been received, I will be able to unblock. Okay, transition to ready, then transition to run. All right, and then what do? I decode the command. All right, so in this case, I have a command and I have a data, so I decode the command, and then from the command I decode the data, and that tells me how fast to blink and so on. Okay, so all the three threads are the same. Okay, the same way they are written. Okay, so in my execution of the control thread, what I do is I first send a data packet 1 to red, then 2 to green, 3 to blue, and 4 to all three together. Okay, so 1, 2, 3, 4. What does it mean in terms of the lab over here? You can see that 1 is to blink for 1 second, 2 is to 0.5, 3 is 0.25, and 4 is 0.125. So it basically giving different instructions on the blinking rate that I want. Okay, so let's compile this code and you will see what will happen. Okay, so I run the code. First, the red LED blinks. Okay, then the green, and then the blue, and then white. Okay, so you can see the rate changes from 1 second to 0.5 to 0.25 to 0.125. Okay, so basically why is it changing is because I am continuously sending different data packets, okay, to the different messages. All right, and for the last one, I send the same message 04 to all three message queues at the same time. So all three wake up at the same time and blink as white. Okay, so that is what is basically happening, okay, for this code over here. Okay, so if you look at it, all right, the way you can actually apply this, okay, the way you can apply this to your mini project, okay, is to have a similar idea, all right, where you say that your interrupt, okay, is triggered through your Bluetooth interface, all right, and then here you receive some data packet, okay, and from this data packet that you receive, okay, so assuming that you send 1 byte data, you decide how you want to allocate the different bits for different information. Okay, and after that you can decide, okay, so this data packet is telling me that I need to move my motor forward. All right, at the same time, you know that if I need to move my motor forward, for example, I must blink front LED, okay, by maybe particular rate, maybe 1 second. Okay, I can't remember now. Okay, at the same time, you also know that you need to start the audio for the very first time. Okay, so I have 3 bits of information, correct? So then you have your task, correct? So you have a task motor, okay, task audio, task LED. Now, do all the message queues have to come from the interrupt? Not necessarily also. Okay, not necessarily also. Why? You can always use one of the other tasks to trigger the other tasks. Okay, that means you can say that, okay, I want to simplify my interrupt. My interrupt only sends to my motor. Okay, but all 3 tasks are still waiting. All 3 tasks are OS, message, queue, receive. Okay, you're all waiting for message. So all are waiting for message, but this message doesn't have to all come from the interrupt. We can say that interrupt sends to the motor first. Okay, interrupt sends to the motor. So what happened? The motor will wake up. All right, and then the motor will say, okay, if it's supposed to be forward, okay, forward means, okay, what do I need for audio? Okay, what do I need for LED? Okay, once I decide what I need for audio, what I need LED, then I say OS message queue send. Then OS message queue send. Okay, so you can have it such that your interrupt triggers one of the tasks. Could be a motor task, could be something else, correct? Or like what we say, it could be a T-brain task, right? Overall task that manages. And then your T-brain task sends to other tasks. Okay, so you can say that instead of T-motor, you can put it as your T-brain. Okay, I think that's what I mentioned in the slides, I mean the handout. Okay, and then that can overall send to other tasks. Okay, so I can say audio, LED, motor, and so on. And then I can send to other tasks from that particular task. Okay, so it's up to you how you want to divide and send the work. Okay, and it doesn't have to be all message also. Okay, you can say that in some cases I can use event flags, correct, or thread flags. So depend on which event flag is set. So for example, LED, correct, I can say, okay, instead of message queue, I don't want message queue, I use event flag or thread flag. Okay, so if bit 0 is set, I flash the front. If bit 1 is set, I flash the back. If bit 4 is set, I flash both of them. Okay, so it's up to you. It's up to you how you want to structure this framework and which tools you want to use. Okay, so the handout gives you some guidelines, correct? So let me bring it up. Let me bring out the mini project documentation. Okay, so in terms of the guideline, okay, so you can see that basically the minimum requirement is you must have 4 tasks and 1 interrupt. Okay, and the 4 tasks is again T-brain to decode the data and perform necessary action, motor control, LED, and audio. Okay, then your interrupt is to capture the serial data coming in. Okay, so this is just a general guideline. I did not give you any specific ways. Okay, so as you can see here is clearly written that you are free to decide the way in which a task will communicate and synchronize. Okay, so you can decide how you want to do it. Message queues, thread flags, event flags, semaphores, mutex, all is up to you. All right, so as you can see, mutex, you use it when you have shared resources that you want to protect. Okay, other than that, semaphores, thread flags, event flags, and message queues can all be used in one way or another to synchronize the behavior. Okay, which one you want to use is something that you can decide. Okay, there is no particular restriction on that. Okay, so think carefully, okay, exactly how you want to go about designing this architecture. I think coding wise, all of you are very good. Okay, there should be no problem in coding, and you have all the sample code also from the lab manuals as well as online. Okay, so coding wise is not the issue. The main challenge, okay, is always getting the architecture right. Okay, so do not rush into it. Okay, last Friday I saw some of you, your code. Okay, you have about like 200 mutex all over the place. Okay, so don't rush in and put everything everywhere. Okay, think carefully exactly which sort of tool you want to use. Whether I want to use Semaphore for this, I want to use message queue for data transfer, or I want to use event flags to synchronize the motor and the audio. Okay, so think about it carefully, and then you decide, and then you start to code. Okay, because once the architecture is up, it's also easy to divide the work among your friends. All right, so you can say, okay, you will work on the motor control, you will use this mutex, you will use this semaphore, okay, and I will work on this and so on. So it's easy to divide the work when you have your architecture already formed up, and each person knows what they're going to use. Are they going to use event flags? Are they going to use semaphores or so on? And then they code accordingly. All right. So think of the architecture, spend some time to discuss it and be very clear about it first, and then you go in to implement. Okay, because if you start coding and then later on you start switching between here and there, you'll waste a lot of time. All right. So discuss the architecture and then you go ahead. All right. So basically today, okay, we have covered what we wanted to cover, and why I wanted to finish up all of this today is because with this, you more or less, okay, with lab 8 and lab 9 manual, you can go through. Okay, it's important that you go through both of them. Okay, so with that, you have a clear idea of all the tools that you have. Okay, and then you can decide what you want to use. Okay, and then your project can go on smoothly. Okay, so until now, you have worked on all the low level stuff, the driver, putting everything together. All right, now it's just the architecture, how to put everything in place so that they can all communicate with each other, they can synchronize with each other, and the data transfer and everything happens smoothly. All right, so that is the last part that you need to figure out with all these things that you have. Okay, so basically that's what I wanted to cover today. All right, on Friday, again, you can come to the lab if you wish, or you can work remotely. Okay, importantly is, like I said, please start to discuss and finalize your architecture. It's already week 10, okay, which means you only have 11 to 3 more weeks, and then it's a presentation already. Okay, so please try to form out the architecture by this week and start to build up your entire code base, okay, for the OS. All right, so thank you very much. Okay, any other questions you have, you can stay behind and ask me. If not, that's the end for today, and I will see you all during the lab session.